So, hello everyone, welcome to the third session of the fourth workshop on proximity perception in robotics. This year's topic is about increasing safety for human-robot interaction using tactile and proximity perception. In this session, we will feature two invited speakers, Professor Hubert Zangl from the University of Klagenfurt in Austria, who will talk about real-time simulation of proximity perception sensors towards sensor system design and sim-to-real applications. And we are also happy to feature Professor Shinichi Hirai from the Ritsumeikan University in Japan, who will talk about fabric-based proximity contact sensors with application to variable stiffness links. Therefore, I would like to move on and start with our first speaker. It is my pleasure to announce our next speaker, Professor Hubert Zangl. Professor Zangl received a master's degree in telematics, the PhD degree in electrical engineering, and the Venia Docenti degree in sensors and instrumentation from the Graz University of Technology in 2001, 2005, and 2009, respectively. From 2010 to 2013, he was an associate professor in sensors and instrumentation with the Institute of Electrical Measurement and Measurement Signal Processing at Graz University of Technology in Austria. And since September 2013, he has been a professor of sensors and actuators with the Institute of Smart System Technologies at the University of Klagenfurt in Austria. His current research interests include design and optimization of smart sensors and actuators, robustness and reliability of sensors and actuators, sensor signal processing, autarkic wireless sensors, energy harvesting, and application in robot sensing and the Internet of Things. So Hubert, we are very looking forward to your talk, and the floor is yours.
Okay, Kirsten, thank you very much for the introduction. I'll try now to share my screen. So I hope this did work. You see my screen now?
Yes, we see it.
Okay, so as already said, Professor for Sensors and Actuators at Alma-Mater University Klagenfurt, and recently I've also started a joint initiative with Silicon Austria Lab, which is the lab on ubiquitous sensing, and this also somehow covers the topics that we are interested in. And let me just show some examples of sensors for some smart environments. This is not necessarily just restricted to robots that we work on, but we have a background, of course, from sensors and integrate them in various environments, like on aircraft wings or blades of wind turbines, or on the bottom you also see here sensors integrated into a steering wheel for stress detection of the human. But one of the exciting topics where sensors are interesting, or of interest, and what we also heard in the presentations already, there is still quite some interest in all these sensor developments is in the field of robotics. And so this is here a very exciting area for us as well. And we aim basically to bring the sensors to where they are needed. That means both physically and logically, they need to be integrated into the environment, and they need to perform the functionality that is of interest there. And considering the development of sensors, basically, of course, this starts really from the low level, from the technology and sensing principles, and then the evaluation of the sensor signals and sensor electronics, and then signal processing inside the sensor. So we have a lot of low-level aspects to be covered, and also the simulation here for the sensor effect, for instance, in the this final element simulation sensor usually address really just the sensor itself. But what has become feasible in the last years is to also consider the higher levels, like the mid-level calibration, sensor fusion, and so on, even up to the higher level that goes all the way to decision-making and task planning, which I find quite important for the functionality of the sensors and the requirements that we have. And so designing a sensor first, then bring it into the application, and then develop the high-level applications, and at the end to find out if this sensor that we have developed is a good device may not be the best approach anymore. And so what we try to do is basically to speed up this loop and not follow this traditional remodel approach. Even in research, when we do hardware development, this is a time-consuming task quite often. that we really have this hardware and all the relevant components realized. So we also want to here have a stricter or a closer interaction with those who are strongly using the sensors on the higher levels, and such that we can speed up the whole development in some sort of an agile process also for hardware development, get a faster feedback, just adapt to what is needed in a better way. And since we cannot always just have all these devices realized and implemented faster, so one approach that appears to be interesting also from this point of view is to bring realistic simulations into system simulations so that we can showcase and discuss such implementations of sensors at an early stage in these simulations. And this is kind of a motivation for us. Whereas in general, of course, Sim2Real has been a buzzword lately, also using simulations here, for instance, in machine learning and utilizing here these experiments that can be done effectively on the computer. But for us, it also goes here one step further, that we also want to use it here in the development process already, and then we can have further benefits out of these models that we develop when they are accurate enough, like model-based control, self-diagnosis, and even virtual sensing can be based on such models. So quite useful from that point of view. Nevertheless, I would like to show one slide from the second workshop on closing the reality gap in Sim2Real transfer robotics. That was on RSS 2020. And quite interesting, even the people who are interested in Sim2Real applications see this sometimes a little bit critical, like more than 20% even consider it as a waste of money and time to go into this. Nevertheless, the majority believes it is useful. And also the majority thinks, okay, this is something new. It's not just simulation, bringing simulations that we have done for sensors, for instance, for a long time, together with the system simulation of the robotic application, and having this used basically for the design of the devices is, at least for us, quite a new approach. What is also debated is if high accuracy is needed for such simulations, and this is not that clear if this is really the case. And I will also go a little bit into this discussion. So our aim is actually to provide quite realistic models for our sensors, for the proximity sensors in this case that we are addressing here. Let's see a little bit on proximity perception sensors that are out there. Vision can be used, of course, also infrared, thermal emission is used in these scenarios. LiDAR, TOF cameras, flash LiDAR at the end are also approaches that are used. Radar can be used, sonar, and near field proximity perception. We had in the previous talk also capacitive and inductive sensors. And then next to proximity then is the touch, which is also here or has been discussed quite a bit, that this interaction with the objects is one of the very big topics right now. And when we look at the visual representation here with these two examples, we see that these things are really, really impressive what can be done here from simulations, even real-time simulations, quite realistic scenarios, and this has been used a lot in machine learning as well. But we want to use basically these tools that have been developed here. Also the hardware acceleration has been developed for these applications for simulating other sensors like TOF camera, radar sensors, and capacitive sensors will be addressed in this talk today. So this nice frameworks not only give us here these visual representations, but usually also can get nice depth images, and then you could practically use this for a simulation of time-of-flight sensors in quite a simple way. So you get basically for your image the distance values. But even for depth cameras, it's not just that the real sensor will behave exactly like this ideal simulation. So there are ideal effects, like we have on the top showing flying pixels that occur on the boundaries of objects, where you can actually get arbitrary values for the distance for these objects by mixing the signals of these objects into reflections. And we have noise, we have interference, we have also effects like shown in on the bottom right, that we have multipass propagations that actually lead then to a wrong distance estimation, because the average time of flight for one pixel is then increased due to this multipass effect. So this is something that we are currently working on. There are already some solutions for these aspects, but I would say this is kind of more straightforward coming from the computer graphics applications. But what we also have addressed are other proximity sensors, proximity perception sensors that utilize basically the same simulation chain out of this computer graphics approaches. You see here an illustration of a scene that gives us practically then the visual image and also the depth image, which we can then take as inputs for this modifications to compute a sensor output out of such a representation. So we can use it to obtain the geometry information, and by encoding material properties, for instance, in the colors, we can also include information on the materials in this way. When we compare now different principles, namely the three types of sensors that were mentioned to discuss today, that's time-of-flight cameras. They are high-resolution sensors. We can more or less see this as single beams per pixel, so we have a clear and high directional sensitivity for these devices and very high number of individual sensors. In the radar scenario, it's not as high resolution anymore. Typically, we have few antennas, and the directivity of these antennas is not like really just a single ray that we get, but we have accumulated somehow from different orientations, and we can still recover something with signal processing and this antenna arrays to recover, for instance, the angle of an object in the field of view when we have multiple objects, but still we have a rather low angular resolution. And this gets even worse for the capacitive sensors, where we have even more blurred results for the scene that we look at. Nevertheless, we can take this chain that we had before to take here the input for a simulation that gives us then a more accurate model of the raw data that the radar sensor would generate and that the capacitive sensor would generate. And now I would like to go a little bit more into detail on how this is done on the example of the radar sensor. General advantages are here, of course, that we have light-independent sensors with the radars that can also provide the speed of the object in the scene, but we have not this resolution that many pixels as we have with, for instance, this time-of-flight cameras. Why won't we simulate these devices? Well, of course, use the data for AI-based methods, but we also can test different configuration sensors that may not even be available yet in such a configuration with this number of antennas and so on. And so we can do studies in advance and basically even decide or contribute to what type of configuration of the radar sensor would make sense. And the simulation approaches like finite element method and the classical approaches are comparatively slow. Ray tracing approaches are also rather slow. And so what we have done basically was then to combine this with this computer graphics approaches, giving us here the depth maps. Quickly, how does this radars work? And specifically, we have been addressing here frequency modulated continuous wave radars. In essence, they send out the beam and modulate the frequency. So the frequency increases over time. And so there is a time delay between the received signal and the transmitted signal, and the time delay corresponds to the frequency difference. And after mixing, basically this frequency difference can be seen, but it's not that you just get one reflection, but basically you get a mixture of all these reflections that we have in the scene, and this then leads essentially to the raw data that we receive. So basically, we have a transmitted signal, a time delayed receiver signal, and the frequency corresponds at the end to the distance. And we can also do then another Fourier transform over subsequent chirps to also obtain the velocity information for this received signal. And in the modeling, basically, we take this image that we get from the simulation, so actually the camera representation is the depth camera, and then from this, basically from all these contributions of all the individual pixels that we would have, the received signal is computed, and the reflections on the surfaces basically follow here comparatively simple model, which has a diffuse and a specular component on this surfaces of the objects. What can also happen with this radar sensors is that non-conductive material is partially penetrated, so you get reflections from each boundary essentially, but not only from the first boundary. So here multiple Z buffers could be used, and then the signal can be combined from the individual distances. So the larger the distance, the higher is the frequency. So at the end we get a mixture, and finally applying an FFT, you can actually again resolve these different components and say, okay, we have more reflections, more distances here in the scene. So this has been included here. For a simple scene here with 3 rods, as it is shown, it was also tested in comparison with real measurements here. Actually, you see here that they are quite nicely resolved, and you get also this point cloud representation. So each of these rods essentially represents one point in here, and this can be nicely resolved in such a simple scenario. Here, every object is clearly distinct from each other, and the simulation and the real scenario have a quite nice overlap, so very similar in the results. The situation becomes much more difficult when we are in more realistic scenarios, like here, a human moving around, and there is not just a single object, but this one object with these extensions and so on gives, of course, a mixture with different distances, and then just assigning more or less one point to it is quite different. And this is not just the case for the simulation, but also for the real radar. And what we see here is that we have quite some variability in both signals. Nevertheless, the general behavior or the general characteristic of both scenarios is quite similar. So even if we would tell the human take the same trajectory twice, there would be a difference between this, and this difference would not be much more than what we have between the real radar and the simulated radar. So still, this is considered a reasonable accordance between the simulated and the real data. And in particular, we have also compared it with other approaches and still get a good match with the realistic, with the real measurement data. And as mentioned, this can also be investigated with obstacles in between that are transparent or partially transparent for the radar signals. And also here we have a similar characteristics, but you see basically that you get an additional reflection from this object in this representation on the left that shows basically where this object and with which velocity it actually is moving in here. So this work basically was presented this year at the IROS. So main contribution of Christian Schöffmann also present in this meeting today. But we are not restricted here to use this same approach from the computer graphics for radar sensors, but we can also use it for capacitive sensors, with the difference basically that the characteristic is even more different, and we cannot use here this ray type approach that we use for the radar time of flight sensors, because we have a much different interaction between, for instance, the human and the the field of the sensors. You see this here on the top left with different modalities. So between two electrodes, there's an electric field. This might lead to an increase or decrease of the capacitance depending on the design of this electrode configuration. And so there are different modes how the sensors can be operated to get at the end an estimate about the distance and location of the object. This can be used if you have multiple electrodes, not just two, but multiple electrodes. This information from these various electrodes can be fused, leading to the electrical capacitance tomography approach. So basically then from a number of capacitance measurements between electrodes, the distribution of the material can be reconstructed. And you see here basically some results from the PhD thesis from Stefan Mühlbacher-Kara on proximity sensors, but also on a grasper sensor. See here, I'm not sure if you can really nicely see the true location of the object and the reconstructed image of the object. You see, it's not a sharp image as you would get it from vision. Nevertheless, the sensors, the capacitive electrodes, they can be easily integrated into the surfaces or even into the grasper, into the fingers of such a grasper, which is an advantage. Nevertheless, this is still a decoupled thing. So we have done this work here in the lab, just the sensor alone, but I believe that there is huge benefit if we could consider much more realistic scenarios, not just such a single rod in here that we have, and also measured, of course, in the lab, but also in the simulation. But we would also want more realistic scenarios to also find out what is a good configuration of the sensor. And this brings us at the end again to the system simulation. And the example that I would like to give here is already presented in 2019 at the IROS for a forestry crane, basically, which has the task to automatically order some logs. And here we also believe in the interaction of even machinery with the environment. It's beneficial to have some short proximity or even tactile information, and to bring here sensors into the grasper of this forestry crane with requirements with respect to this harsh environment that's out there. But again, we started here with the simulation and used the same approach basically to get from the robot simulation some 3D representation of the geometry, which we then used into applied for a finite element simulation with some approaches to speed up the whole computation, like avoiding remeshing, for instance, such that this can be fast enough at the end. So this is a similar approach, and here we should, if it runs, okay. See some results here. So basically the log is grasped here, and the capacitive sensor inside the grasper, of course, detects here, due to the higher permittivity of the log, the capacitance increases. And this can also be done here with multiple sensors. And then basically from this multiple sensor information can be inferred how the log has been grasped and if this was a successful grasp or not. So this was scenario for an industrial application, considering a crane as a robot somehow, but also this can be done for interaction with humans. So this is here another work from Christian considering a model of human hand, and the sensor has actually in this case been built before. So in 2020 presented a gesture-based contactless control of a robot. So you could use gestures basically to control the robot. But here after that it was shown, okay, this simulation framework also works here for this gesture control. So basically you see with the increasing distance, the capacitance for the red electrode is decreasing, for the blue one increasing, and at the end, there will be also some motion and then between the phase shift or the phase, the signal delay that we have between the blue and the red signal, then the orientation of the movement, also the velocity can be used then to realize the gesture-based control, which has been done in this scenario. Okay. So at the end, such a system of a capacitive sensors, we can model it, we can do some lab tests. It's also intended, of course, for the use with human-robot interaction. So there has been some work with the colleagues also from Chemnitz and Karlsruhe regarding assessing the performance of capacitive sensors. So for different parts of the body, the characteristic of a capacitive sensor is different. And Serkan Ergun, who has also been driving a lot of the work on our side, I will give also some more deeper insight into this in the PhD talk, because he's working here in the area of looking into safety connected with the proximity sensors, like the capacitive sensors, how we can use this, for instance, for power and force limiting even before the contact has already occurred. So I have one last thing to more or less close the gap or close to the initial thought that we want to have some sort of agile development switching between real application and simulation. So we also work on this transition basically between how can we then, once we have decided, okay, in the simulation we have a good architecture, quickly realize the sensors. So we have also the same interfaces more or less for simulation models and lab models, and how to access, for instance, a sensor, how to bring a sensor into the system is governed here with some sort of an electronic data sheet that helps us basically to speed up the process and maintain the information and exchange really between data that comes from the simulation and data that comes from the lab model. So here on the left, top left, you see the simulations that you've seen before. Just below, you see behind the cage in this case, because at this point it's not safe, the lab model of the grain. And here we can say, okay, the sensor simulation, of course, has existed much longer, much before the actual sensor has been realized and integrated into this grasper. So with challenges, this can freely rotate. So this is at the end a wireless sensor that has to be implemented. And this also shows, okay, we can do investigations much earlier and even bringing the, relevant knowledge from the application into the sensor design. And so this is really a driving motivation for us. It's that we, of course, want to use the simulations at the end to realize sensors, even also with integrated circuits, bringing this into the sensor assembly, then bring it on the robot, and then use this in the robotics application, but to avoid basically to do this in a sequential approach. But you can do this work on the sensor development, but also on how to use the sensors in parallel. So summing up, would say that with the progress also in computation GPUs and so on, that can be used for computer graphics and also for fast realization of finite element methods. We have now reasonably accurate sensor simulations that are fast enough to be included in robot simulations, or the other way around. We have accurate sensor simulations that are reasonably accurate to be included for such investigations, such that we can use this in the sensor design phase, this information that we get there, but also in this machine learning approaches, the quality of this should be good enough. We also can think about doing things always sequential, design the sensor, then maybe do some signal processing, even with machine learning for the sensors, for instance, eliminating in this time of flight sensor that this flying pixels or whatever, or in the radar sensors, we could also try really to get then point clouds out of the radar sensor, because this is more common way to use 3D representations. But when we do this link along the full chain from really low level to high level, I think we can benefit a little bit as at some point when we reduce the information, for instance, from the radar sensor to just a single distance and a single location of a human, we lose information. And so I believe that if we can maintain it as long as possible, that will be helpful, even though, of course, it adds a little bit to the complexity. But nevertheless, having all this into one common simulation framework, this should help that such approaches are feasible at the end. With respect to accuracy versus reliability, of course, one thing is we need to validate also this sensor simulations. We bring in, of course, the knowledge that we have from the behavior of the sensors and see, okay, what are these non-ideal effects? But at the end, we often have still some variability difference between, for instance, also one setup to the next, which we also have in the reality. And so this is also what has been debated for, even for vision-based algorithms. If the scenarios that we investigate have a huge variability anyways, then maybe it's not necessary to be that accurate for the individual scenario. But at the end, we need to cover, of course, the whole distribution that can occur, and still all the effects should be covered. That's what I am pretty convinced of. And nevertheless, we have still a lot of effects and also not all sensors that are fully covered in all the simulations. So we still have in all these areas, time of flight, radar, and capacitive sensors, still things where we need to improve and move forward. And things become even harder, was also mentioned in other presentations before, when we include here also the tactile sensors and the interaction with the material and maybe even deformable materials. So there's quite a bit of work ahead of us in that area. Of course, I have to thank a lot of contributors. Some of them I mentioned in the talk, like Christian, Lisa, but also the team is, of course, very important. The partners are very important in here. And we have the material, the videos that I've showed also online. And I just would like to point out that the radar simulation is open source and available, and there is still work to do. So also contributors and users and feedback is very much appreciated. So I hope also that this finds your interest and feedback. And this brings me pretty much to the end of this overview on simulation of proximity perception status. As I said, still something, some work to do, something that we can show already, and some more things hopefully to show in the future with my active team. But as I said, we're also very happy to collaborate, like as Catherine mentioned before, so that Christian will have a collaboration there. Good, then thank you very much. I'm happy to answer any questions if there are some.
Thank you very much for your interesting talk. So, questions from the audience. If you have questions, please just raise your hand. Yes, first question I got here from Kasper.
Yeah, thanks for the very interesting talk. I like the extra explanations on radar. I think I learned quite a bit from that, so that was very nice. You used the term sim to real, and you said it's kind of a buzzword. I was expecting you to use also the word digital twin, but I think you didn't use that. Why? Or is there no relationship between what you're doing to digital twins as well?
Yeah, actually, I had remove the term. I had it in the presentation initially, but sometimes it leads to confusion what a digital twin exactly is. So there are different interpretations. So when we talk often about a digital twin, it's like with a representation of a system. You have some industrial facility that runs actually, and you have sensors that gather some information out of it, and then you build digital twin of this facility based on real sensor data, so cyber physical systems, and then basically having this digital twin. When I talk, or we talk about digital twins of a sensor, it's more the simulation model that we talk about, and bringing here realistic results. So the sensor model behaves exactly the same way as the real system, and then basically the real system, including the sensors, behave in the same way. So yes, actually, we often also use the term digital twin here. I just thought a little bit, okay, maybe it's confusing.
So if I understand correctly, at least some part of your work looks at just making a very good simulation of the sensor and does not need the real sensor then for the process that you're going through, like developing a sensor.
Yes, so the idea is basically, on the one hand, for instance, if there is a sensing modality that we could think of to investigate, okay, what's the benefit for the application? Or if we have our tool set of sensors that we have, like time-of-flight sensors, radar sensors, capacitive sensors, and we want to configure sensors or the robot for a certain application, would like to find out, okay, which sensors should be there, which are useful in the application, where should they be located, how should they be configured, maybe some of them are not even needed, or the signal can then be calculated in some sense of virtual sensing out of a good simulation based on other sensors. So this is then something that can start quite early. Also, the further use of the sensor and the high level can already be based on the simulated data. Yeah. And we can basically then in parallel realize the sensors physically. So this is maybe one aspect, and we can, let's say, capacitive sensors, they have quite variability in how the electrodes are designed. So there's not just one sensor, but we have different architectures, and they have then different characteristics. And so we have a huge design space at the end, and doing this exploration really in the experiment. Yeah, a lot of papers that compare at the end different electrode configurations for applications is of course very time consuming. If we can do this earlier and in the simulation, and then basically realize what works best for the given application, which is often quite different, different distances needed and so on, and different materials involved, this can speed up the whole procedure quite a bit. That's at least what we believe, why we're following this approach.
Yeah, no, very good. I just have another question. So I'm interested in capacitive sensing, but I'm also interested in optics-based sensors. We have developed sensors based on optics to measure tactile information, but also proximity. So I'm wondering whether you have any experience in that area, modeling those?
Not really. Yeah, so I'm now, as I could say, the only, let's say, optical based principle so far that we have been investigating is time-of-flight cameras, which has, of course, some relation, but not really much on classical, traditional optical or vision-based sensors. So we have usually all the sensors that are more complementary to vision, and we also have not at least because we also have colleagues here that are more addressing the vision-based approaches, and so yeah, it's a little complementary to the work of the colleagues as well.
Yep. Okay. No, just was wondering whether you had some experience there, but yeah, thanks a lot. Thank you very much.
All right. Then next question I have here is from Yital.
I think Stefan was earlier.
Okay, then Stefan. I don't see any ordering. Sorry for that.
Yeah. Well, I will just ask my question. So yeah, I was wondering if you, so when you talked about sim to real, if you have any insights already, or what are your perspectives on reinforcement learning? So when we talk about sim to real, we also immediately think about reinforcement learning. So do you have any perspective on, let's say, grasping tasks or something like this?
Yes, I mean, clearly this is something that is of high interest, and basically to use this approaches also in there. But here I would say we are really, or at least from my side, this is in the beginning stage. So we're doing this, of course, with the partners that have a lot of expertise in this area, and so I think this is a way to combine basically also along these different levels, right? So we can contribute here with quite accurate simulations, have a physical representation of what's out there, and then basically we make the link and see, okay, how does that then work when we include this into this reinforcement learning approaches and so on. But of course, this is one of the applications that are here very important, and so this is definitely something that's being more in the focus in the future.
Okay, thanks.
All right, thank you. Then Yitao.
Yeah, thank you, Hubert, for your presentation, first of all. I was wondering, simulating electrostatics like capacitive sensors is possible, as you said, with FEM solutions, but capacitive sensors or electrostatics depend on so many parameters, like not, if, for example, the example you've given with the log, grasping of the log, it depends on the humidity, type of wood, type of, I don't know, so many parameters. Even though if you can simulate the sensor itself, it always depends on the environment. So do you think if for capacitive sensing, at least if sim to real, if this is feasible or not?
Actually, I think it is. I mean, for several reasons. At the end, yes, of course, the material property is relevant of the log. But for instance, in this application, still the dominant effect is the distance and the shape, because the permittivity or even the conductivity, which is also relevant, of course, for the capacitive sensor, is much higher, significantly higher than of the environment. And then you can use it, or you can reconstruct even to some degree a geometry as with the capacitance tomography approach. What is of course critical for capacitive sensors, if you have some like a water film or whatever directly on the surface, yeah, this you need to somehow avoid basically. But usually, yeah, if there are small drops, it's not an issue. But if you have contaminations then on the surface that stick to the surface, then you have a problem with the capacitive sensors. But you would also have with other sensors, optical sensors will not work when there is contamination. Like other radar sensors to some degree can penetrate. So yeah, I think that it's at the end, again, a combination of multiple sensors that makes then the best result. Nevertheless, in many situations, I'm pretty sure that the simulations are pretty close to what you have in reality. And this negative effect, so this as you mentioned, varying humidity, condensation, and also different material properties. This is something in developing the algorithms or whatever, we should also include this variability into the scenarios. So we need to add all these effects also into the models. We don't know what you have then in the concrete specific situation, but when you have developed the algorithm to work under all given circumstances reasonably well, then you have a good chance that it will also work. So that's why I'm quite sure also for capacitive sensors that this will give us a good result at the end.
And do you think that could it be more challenging to even develop the models for the environment compared to the sensors? So the sensors are actually, they are pretty well defined. So you have certain shape of the sensor, you maybe know how the how the electrostatics spread out according to the sensor shapes, but the environment, I think it's very hard. It will be very hard to describe.
Well, it's a matter probably of abstraction. So how far do we have to go, basically, with this? It is for sure not easy to reconstruct everything much or very accurately, but the forward simulation, like if you know geometry, whatever, to compute then the capacitance values accurately, I would say this is okay in some sense, because the material properties, they are not that dramatic for the proximity perception applications, because still the air with the low permittivity is the dominant vector, and the other variability that we have, that's what I said, we don't know exactly the material property of the log, depends even on the weather conditions, if the permittivity is higher or lower. But still, this can be covered, in my opinion, sufficiently well, so that the time now for really realizing sensors, putting all the electrodes maybe into whatever, a grip that has complex shape and so on, I still think simulating is faster.
Thank you.
Okay, so thank you very much, Hubert, for your interesting talk and the insights in your research. And now I would like to hand over to Caspar to introduce our next speaker.
Yep, thank you. So it gives me great pleasure to announce the next speaker and introduce the next speaker. It's a very good colleague of mine, Shinichi Hirai, and he is at Ritsumeikan University in Japan. And he is a professor of robotics at the Department of Robotics at the university there. And he's leading the soft robotics lab activities and very much focused, obviously, on soft robotics, and has a particular interest in sensing and actuation. And so he, has developed numerous systems and contributed a lot to the field of soft robotics. So it's soft sensors, pneumatic systems, and always with a view at developing systems that can also then interact with the physical environment. He also takes inspiration from biology through biomechanical modeling. And he has applied his techniques, his approaches to very many areas. So, for example, the food industry, where the manipulation of food is very important. But he looks also at interacting with other difficult types of objects like clothing, and has even developed locomotion systems. So today he is talking about fabric-based proximity sensors, and that is, of course, of great interest to me, and we have been collaborating for quite some time on that topic already. And so he's looking now at these fabric-based sensors and how they can be integrated with robotic structures, and in particular stiffness controllable links. So that is something that's very much at my heart, it's very much linked to my research. So I look really forward to hearing from Shinichi about their newest research in that area. Thanks for coming, Shinichi, and I pass over to you now. The floor is yours.
Okay, thank you very much. So I will share the screen.
Yeah, I can see you. Yeah, perfect.
Okay, yeah. Okay, Caspar, thank you very much. So here, I'm talking about the capacitance based on the sensing, and also I will introduce some sensing algorithms to cope with the change of the environment. Okay, so here I'm talking about fabric-based proximity contact sensors with application to variable stiffness links. Okay, so first let me show what I've done here. So Okay, so this is here's the variable stick link. So covered with the fabric sensor. So the fan, hand approaching to the link, this link reduces its stiffness. So by reducing the inner pressure, and also the hand, okay here, and also the hand departing, the sensor, the sensor recovers, the link recovers its stiffness. So by increasing the inner, the pressure. So now, we can control the stiffness of the link. According to the approaching the target. Our approach is just to combine soft bodies with soft sensor skins. The bodies here, the variable stiffness links, they developed the King's College London and Queen Mary and Queen Mary University London. And here's the sensor skin. We have developed at Rhythmic University. Now we have combined these variable stiffening rings and also this fabric sensors to realize the safety for human robot interaction. Okay, but first of all, let me talk about the variable stiffening links. This link consists of the inner rubber tube and also the outer fabric layer. When air pressure is applied inside the link, the inner tube will expand, causing the contact between the inner tube and also the outer fabric. Increasing the friction between them. Then the stiffness will increase. When you reduce the inner pressure, we can reduce the stiffness of the link. Okay, here's the fabric sensor. Basically this is a very simple one. This is the conductive fabric, in market. This fabric consists of plain. This fabric is a plain knitting of conductive and non-conductive yarns. The good thing of this sensor, okay, this is a fabric. This is bendable and also somewhat stretchable. It means that we can attach the sensor, this fabric sensors to soft bodies, and also the measuring the capacity. We can apply many principles, resistance based, capacitance based, and so on. But here, we applied capacitance, measuring. Just by measuring the capacitance between fabric and the approaching target, we can estimate the proximity and also contact the target. Just by replacing the outer fabric of a variable stiffening link with this fabric sensor, conductive fabric, we can construct a variable stiffening link with a fabric sensor easily. Okay, so here's the sensing principle. Here, if the target is far away from the sensor, the capacitance value is almost the same. Basically stationary, basically in stationary. But when the target is approaching the sensor, the sensor value will increase. And also, the target is in contact with the sensor value will jump up. Just by monitoring the sensor the output, we can determine if proximity of the target happens and also the contact with the target happens or not. to realize such a detection, so the first we will determine the reference, so the capacitance, so the nothing, so the is nearby the sensor. So this is the reference. So the based on reference, so that we determine the two thresholds for proximity detection and also the contact detection. So the problem is, okay, how to determine the reference capacitance. Okay, so here sensing method. So just by comparing the capacitance output with the two thresholds, so that you can determine the contact happens or so the proximity happens. So because this is a simple implementation with this algorithm. So this is the first demonstration. Okay, so this is a simple rigid links. So the two links. So covered by the two fabric sensors. So the one problem happened here. Okay, so this is the desktop. We will show if the proximity of the contact happens or not. So here, you can see here, even though the target is approaching to the link system, so the algorithm determines the proximity or contact happens because the two links are moving the closer each other. So it means that if we determine the reference the capacitance and also the two thresholds determined as one, the reference capacitance and the two thresholds, we cannot cope with such the motion of the robot links. So in addition to the motion of the capacitance is affected by motion of robot links, and also in addition to the robot motion, the capacitance depends on the environment, so the obstacles and temperature and the humidity and so on. So many the issues will affect the capacitance. So the problem is, okay, even though we have no the target, close to the sensors, so the difference capacitance may change according to the motion of robots and also the change of environment. So this suggests us, okay, the reference should be updated according to the motion of the robots and also the change of the environment. Okay, so this is the idea. The ideas of how to cope with the motion robot links. How to update the reference the capacitance. According to against the robot motion. We assume that, okay, we can obtain the link motion using internal sensors, for example, encoders. We can measure the joint angles, using joint angles of the robot, by using encoders. Okay, but first of all, we use measure the capacitance, the capacitance values, under the robot motion. We will the records the outputs, two outputs. I mean, the sensor capacitance sensor values and also the internal sensor values, and also the relation. The relationship between the two sensor outputs, is summarized into the lookup table. Then the reference at one given the internal sensor value can be picked up through by searching the lookup table. This is this can be a reference value. Next, here how to cope with the change of the environment, how to update reference capacitance. so the against the, so the change of environment. So the here, so the we assume that environment change is slower than the target approaching. Of course, so the sometimes so the sudden change of the, so the environment may happen, but so the after that, after sudden change, so the environment is somewhat stationary. It's an assumption. So the we'll monitor the average and also the variance of the capacitance values over a given period. If so the environment change happens, so the variance, so the variance will so the can be bigger. So we'll update the reference to average value when variance. When the variance so they exceeds a certain value. So by so the implementing, we have implemented so these two algorithms into one so the sensing algorithm to cope with such so the to update so the reference capacitance. So the against so the motion of the robot and also the change of the environment. So here's one demonstration here. So here, so the okay, you can see here, so the here, so this blue green line, so the red line shows us the two thresholds. Now, so they are changing according to the motion of the so the robots. So we have already so the recorded the so the relationship between the so the encoder. Here we have an encoder here. So the at so the joint, and also the capacitance outputs to outputs. Then so the we can so the compensate so the motion of the links. Now here so the human hand is approaching. Then we can detect so the proximity and also contact, as shown in the so the top right, top left. Now, so the okay, now so the we have so the two obstacles here. Now so the we have a so the sudden change of the environment. So because that's for a while, so the okay, so the sensor so they will so the detect the so the proximity of the so the and this so the obstacles. But after that, so the after a while, so this system so they can so they cope with the new stationary environment with obstacles. Then so the now so the okay so the reference so the has been updated, and now so the okay so the sensor system ignores the so the obstacles in environment. But so the human hand so the approaches and touches to the so the sensor system can detect the proximity and the contact of the human hand. So the using such so the update algorithms of the sense reference capacitance, we can cope with so the motion of the links and also the change of the environment as well. And also we can, even so the we can so after removing the obstacle, so the okay the sensor system can so the adapt to the so the change of the environment. Okay, so now so the we have so the applied so this so the fabric sensor and the sensing algorithm to the so the variable stiffness link. So the okay here shows us so the one demonstration. So the here the one so the variable stiffness link covered with the so the fabric sensor. So the you can show the capacitance variance, so the pressure, so the inner pressure of the so the link. So the you can see here, so the okay, so the human hand approaching to the so the target to the so the link. so the inner pressure, so the decreases, and so the link, so the reduces its stiffness. I'll show again. So, okay, so the pressure reduces. After that, so the pressure, so the increases again. So now, so the stiffness, so the can be controlled, so the according to so the approaching and also the contact, so the human hand. Okay, so also now we're testing so the Turing system. So now we have two variable stiffness links. So with this fabric sensors driven by one servo motor. Okay, so even though the two links are crossing each other, we now change the reference capacitance to avoid the influence of the motion, robot motion. But if the human hand touches to either of the link, the system will stop. So the fabric sensor detects the contact, and also the system will stop. Okay, so through such experiments, we find that the inner pressure of the link affect the capacitance value. So here one experiment. So how capacitance will change. So according to the inner pressure. So here the capacitance value will change. So according to the pressure, especially near the contact. So around here 1 centimeter means very close to the target. Target is now very close to the sensor. So it means that we have to now we are considering how to cope with this phenomena. How to compensate how to compensate the effect of inner pressure. Okay, here's the conclusion. Now we have developed variable stiffness link. The links with fabric-based sensors, and also we have developed a reference update algorithm. To cope with the robot motion and the change of the environment, and also experimental validation of safety control. Here's the ongoing issue. Adapting to the inner pressure of the link, and also experiments using the robot arms consisting of multiple arms. Okay, here's the experiment. This work is supported by the Kagenshi project. And also for more details, please visit the website. If you have any questions, I welcome any question.
Yeah, thank you very much, Shinichi, for the fantastic talk. And
thank you very much.
Round of applause. Yeah, thanks a lot. Yeah, no, very good to hear about your work. And I have a number of questions myself, but maybe I ask you, Tao, to start with the questions.
Yeah, thank you very much for your presentation. I really like the variable stiffness approach because recently I submitted a paper or published a paper at ICRA 2021 with a similar approach, but not for soft robotics. So we're using the proximity information to change the impedance of the impedance controller
Okay, I see.
in a normal collaborative robot. So if you get close, the joints will get softer, so to reduce impact. But I think with soft robotics, I see another application with your design. I think it's possible to attach like a skin onto the robot, and if something is about to impact, you can actually blow up the skin, yeah, or like an airbag. Or if it's already blown up, you can maybe open a valve, and if you get in contact, you can release the air out to increase dampening effects. So, so that's very interesting for me. And also in regards for the compensation of the base capacitance, I think the idea of combining maybe Hubert's sim to real approach would also be interesting. So maybe you can have some kind of simulated environment that runs in the background, and with that information you can maybe compensate the environment from the capacitive reading.
Okay, thank you much. So thank you. So one good thing, so the fabric sensor is okay, we can copy the deformation and also the kind of the motion of the among the links. So even though the sensor can be covered by such kind of the elbows, even though if your motion like this here, the sensor might be expand or shrink or something happens. So the fabric sensor can cope with such kind of can cover the joint or kind of the other part, the other joint, with the relative motions. I think this is one advantage of the fabric sensor. So this is not only bendable but also extensible, stretchable. So this is one I believe. So this is one good advantage of the fabric sensor.
Yeah. Do you think if it's robust enough, for example, just to reduce impact? For example, if I have a small balloon inside inside it, and then if something comes close, I just blow up the balloon. And do you think it's enough, robust enough?
Yeah, I think so. Yes, it's of course we have. I've not tested it, but I believe the fabric sensor is very first of all robust against the contact of some kind of the impact. So because this is a simple fabric, okay. So we have no the electrodes or something inside the sensor itself. Of course we have also the wiring, around the sensor, but the sensor itself is also the fabric, a simple fabric. And also we can for example we can stack the fabrics. To have a more thicker the sensor to robust against the impact, the contact. I think we can cope with cope with such kind of we can build up a sensor system which is robust against the impact the kind of somewhat contact with the obstacles.
Thank you.
Yeah, okay, thank you. Maybe I can have a follow-on question there. Good to hear that you feel that these sensors could be, for example, used on elbows, and one could calibrate them to handle that. But how far can we go with fabric? I mean, could they be also integrated with very commonly used soft robots made from silicone rubber. Do you think that is also an opportunity?
Oh, this is a good question. So I think so, but okay, instead of fabric, kind of stretchiness, somewhat limited. So silicone, expand more, maybe over 100% or something. So this fabric sensor has such flexibility. I mean, such stretchability. So of course, the fabric sensors have less stretchability than the silicon-based bodies.
Yeah.
So maybe you have to design. Maybe you have to redesign the sensor system. Of course some parts of the fabric, but for example, some parts are something more flexible, more stretchable part, material made of materials, kind of combining with the fabrics and also the other materials.
Yeah.
It's kind of good challenge of future.
Good challenge, yeah, definitely. I have another question, and I asked that also earlier in our earlier session. Spatial resolution is, of course, always very interesting for all kinds of skin sensors. My understanding is that per link you have only one piece of information that you get. Any chance of improving that, having a better spatial resolution?
So not the capacitance based, but in the resistance base, we have also tested the resistance based sensors, fabric sensors. So just by measuring the resistance, the fabric, we can detect the contact or not. We have also maybe we have tested how to say, kind of multiple. We have asked one fabric company to make a fabric, but with many sensor islands. I mean, the sensor conductive parts are isolated each other. Then we can detect multiple contact. Because I think also we have a limitation. On the fabric, but the fabric company also has many techniques. They have many good techniques to for example, the mixture to fabricate to fabricate one fabric. They using multiple ions, multiple threads, and also some parts are it's also kind of a distributed one. It means that this part is made of something, this part is made of some another fabric, this part is other things. Maybe introducing such techniques, we can increase the resolution, the capacitance sensor as well.
Okay.
Of course, the capacitance based one. Of course, we have the kind of correspondence, kind of crosstalk among the sensors. Maybe you have to develop another the capacitance, the tomography or something. Introduce techniques.
Yeah,
but we have a chance, I think.
Yeah, that's good to hear. And when you say that, you're speaking more about tactile sensors, or you think it will also work with proximity sensors?
Yeah. They both.
Both, yeah. Okay, good.
Yeah.
Yeah. Good. Thank you very much. Any further questions for Shinichi? Not at the moment. So thank you very much again to you, Shinichi. And I think I pass back to Christian.
Yes. So thanks again to all speakers and also to the audience for the interesting discussion and for the interesting question. Our next session will be the PhD forum and will start at 3 p.m. Central Europe time, so in about 12 minutes. So of course, every one of you is invited to join this session. We will have 4 talks from PhDs all over the world talking about their PhD topics. And then after the PhD forum, we will have another session where we would invite 2 speakers, namely Professor Zachary Erickson and Professor Lorenzo Iamone, who will also give invited talks today, and then we will close today's workshop. So thanks to everyone who joined now this session. Important information to the speakers. So the video editing and the video cutting will be done by the organizing team, so you don't need to spend extra time on that. And we will then inform you about further steps for the on-demand platform access and also for the video upload. And our live session of the workshop will be held on the 27th of September, where we'll then feature a 2-hour panel discussion about emerging topics in proximity and tactile sensing. And with that said, I would like to thank everyone. Have a good day. Enjoy your day, evening, morning, and bye-bye.
Thank you very much. See you later. Bye-bye. Bye.
Bye.